Hello, everyone. Doing okay. How are you all? I understand. All right. Tired. Tired is what happens towards the end of the week. Okay. So today we are going to be focusing on the beginning of chapter 14. Okay. For us, it is mostly having to do with vocabulary and definitions. Okay. We should be able to cover 14.2 today without any trouble because 14.2 happens to be fairly short. All right. There's one main idea, and then after we understand that main idea, there really isn't much more to say about it other than just do some pretty straightforward exercises based on things you should be familiar with. Okay, so last time we introduced the idea of a function of two variables. And the idea is that we have a domain D and for the purposes here, we're going to have a codomain R. Okay. Now, we're going to say that this domain is a subset of two-dimensional space, which is what that this symbol here means. Okay, it's more. So there's two ways to write this. This means subset. This means element of. Okay, both are used. Usually, this is the one that you use if you're talking about something that is a single member of. Okay, is most how it's most commonly used, but it can be used in other contexts. And then this means that this collection of things is contained in this collection of things. All right. Put that over there for now. Okay. And the idea is that we have some function f that maps our domain into our codomain. And as we are familiar with, of course, there is some set of, sorry, f represents some kind of relationship that does the assignment of the elements of D into R. So for the purposes of making things fairly straightforward, what we're going to say is that the ordered pair xy is an element of D. Okay. And what we're going to do is we are going to assign to the variable z the value that is returned by f of xy. Okay. Importantly, we have two independent values here and one dependent value. I'm going to raise this up. Leaning is bad for your handwriting, it turns out. Anyway. Okay. So this is going to be how we think about this. And what we're going to end up with is, if we write this in vector notation, a correspondence between these ideas. The vector represented by xyz is going to be equal to the vector represented by xyf of xy. Okay? And so the reason, of course, that we are careful about talking about this is because this gives us a different type of geometric object than what we were working with in chapter 13. In chapter 13, we had one independent variable and three dependent variables. What that gave us was a curve in space that was parameterized by a single value. Here we have something different. Our domain is going to be something that is a subset of two-dimensional space, so down on the xy plane. And above this, we're going to have some surface. So for a point xy down here, it is going to map to some value f of xy up there. So the function value that we get is going to be indicative of height. And this here is referred to as a surface. All right, any questions about that so far? Seems okay? All right. Now, one thing that I want to mention now, and I will probably mention again in the future, just to make sure that it's very clear. We have reached the point in the class where we have to be paying attention to how many dimensions something has. Okay, and there are a couple of different ways to think about this. All right, you need to make sure that you understand both, but it takes a little bit of getting used to, because in your day-to-day experiences, you tend to conflate these two things without realizing that you're doing it. Okay, it's not your fault. You're not wrong. It's just that no one's pointed out that this is important. Okay. In this example here, we are talking about three-dimensional space, right? How many dimensions does this object have? It has 2. Okay. If I'm traveling on the surface, there are only 2 directions for me to go. Okay. I can go basically north and south and basically east and west, right? Now I'm subject to the topography of the object, right? It might have hills and valleys, but I can only choose to go north, south, east, or west, or some combination of those directions. That means that it's two-dimensional. If you had a piece of paper or something a little bit stretchable, like a little rubber sheet, okay, you could take something that was a flat rubber sheet and stretch it into this shape, right? Assuming that you had some way to get it to hold its form. if it was stiff enough to do that. Okay, that means it's 2D, even though we need 3 dimensions to make sense of it, right? Because we want to understand the idea of height. So this surface and the objects that we're going to be talking about in general under these conditions with a 2-dimensional domain are 2-dimensional objects embedded in 3-dimensional space. Okay, the surface is 2D, but in order to be able to display all of the information about that surface, I need 3 dimensions to describe it, because 2 plus 1 equals 3. I need 2 dimensions to represent the domain. I need a 3rd dimension to represent the codomain. Make sense? Okay. Now, in comparison to this, we also talked about space curves. How many dimensions is that object? That's 1, right? If I'm on the curve, I can only travel back and forth, right? I can just follow the path. Think about it like a highway. You can go forward and you can go backward. Those are the directions. Okay, one of those is quite perilous if you're on the highway, but those are your only choices without breaking the rules, right? Now, we're in the same kind of situation here where the parameter in this case is actually kind of hidden because the parameter exists on the line itself, right? We cheat by encoding 4 dimensions into this picture. At any given point in time, this is the picture, right? I need 3 dimensions in order to encode the location of the point. I use up all 3 of them, right? But each time I choose a different value for t, I get to draw another dot, right? So we fill in the curve, and technically that gives me the ability to represent that 4th dimension. Because 3 of them are being used up by the locations, I'm just cheating by doing a fake time lapse by drawing a solid curve. Okay? So there's actually 4 dimensions here. So we have 1 plus 3, which follows what we were talking about before. Okay? Most of the time, we can't do more than 3 in a way that's easy to understand. Okay? Since this curve is parameterized by 1 variable, that makes it a little bit easier. But in general, if the number of dimensions of the domain and codomain add up to be some number larger than 3, we have to do something else, right? We have to start using color, or we have to start using time lapse, or simulating a time lapse like we have here in order to represent those extra dimensions. And it gets harder to think about, okay? And that's when it becomes even more important that you understand the dimension of the object in question and how many dimensions you're using in the schematic that you have made to represent that information. Okay? Now, textbook doesn't go into that level of depth about this stuff, okay? But it's harder if you don't realize that that's what's going on, okay? At least in my opinion. I'm an information up front and sort it out later kind of person, instead of teaching you something that's wrong or incomplete and then having to go back and fix it. Okay? The second one's, to me, irritating because it would irritate me as a student. So I try to avoid that. There's already enough times where things come up where I have to tell you that other people in other classes have lied to you about something, and I have to fix it anyway. Anyway, like division and subtraction, those don't exist. Okay. I'm getting confused looks. All right. I'm 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 making a joke, but that's actually the truth. Okay, so as an aside, addition and multiplication. Okay? We believe in addition and multiplication, these things are okay, right? Now, subtraction and division just exist as counterpoints to addition and multiplication, right? If I write a minus sign, say I write 2 minus 3, okay? What this really means is add the additive inverse of 3, okay? I don't need a subtraction operation for this to make sense. It's just a shorthand way to say add the additive inverse. For multiplication, it's the same thing. Multiply by the multiplicative inverse. Okay, we don't need subtraction and division. They don't exist. Okay, and I actually had a student in another one of my classes who asked me a question about the order of operations because they were confused about something. There was some operation that looked like this. Sorry, that's not right. It was a programming class that was written out just horizontally like this. What's the answer to that question? 0, right? Now, if you are familiar with the mnemonic device that is typically taught to people about how to memorize the order of operations, this means parentheses, exponents, multiplication, division, addition, subtraction, right? This student thought that because division comes after multiplication, that you should multiply first. But if you multiply first, you get 6 divided by 0, which is undefined, right? But that's not how it works because multiplication and division are actually the same thing, right? They're not separate entries in this deal. So I stand by my statement. Division and subtraction are unnecessary. Okay, if you really understand what's going on. It's just we don't teach that to elementary school students because we have to teach them about negative numbers and fractions and all of that stuff. When the first thing that we want them to be able to master is whole number arithmetic, right? So this is one of those instances where you are lied to and then they go back and fix it later, right? Yes. Well, no. So for the purposes of this video, and I don't want to spend a lot more time on this, but this expression, multiplication and addition, both have associative and commutative properties, right? Because of the associative and commutative properties of addition and multiplication, we can add and I can have a sequence of additions that occur in any order or a sequence of multiplications that occur in any order. Okay, so this statement, even if there's division operations in here, has to make sense and obey the associative and commutative properties of multiplication. So you don't do it the way that it's written down because it's written down that way. You can do it in any order. And so what you don't want to do is make some mistake in writing it that that makes it look like there should be parentheses somewhere where there's not, right? Because the mistake would be to think that there's a set of parentheses here for some reason. And that was the mistake that the student made because they assumed that there was some implied order that multiplication has to happen first. When no, it's all multiplication. No. Someone here said something about the whole number arithmetic way of thinking about multiplication, where you can represent multiplication as repeated addition. So like 2 times 3 would be 2 plus 2 plus 2, okay? Or 3 plus 3, right? You can do either way because multiplication commutes and associates. But that doesn't work if you don't have whole numbers anymore. But you need fractions and all that stuff. This is not an algebra class, but the deeper answer to the question about why multiplication is necessary along with addition is the realm of algebra. Okay, in order to construct the algebras that we are used to working with, like integers and rational numbers and the real numbers and complex numbers, multiplication and addition are both necessary, and they have certain properties. Okay, when they don't have certain properties, then you start getting things that don't have the algebraic properties that we're used to working with, which is a conversation for another time. There's a class called Math344 that's about this, if you have interest in that. I think that's the number. It's fundamental concepts of algebra. I'm making finger quotes. Okay. The words fundamental and elementary in math are a little bit anxiety inducing. Okay. So let's get away from that discussion for now. All right. So if we switch to our notes and take a look at some of the figures and examples here, all right, this is an example of a three-dimensional image. Okay. Now, when it comes to working with these higher dimensional objects, there is a balance to be struck between driving yourself crazy trying to sketch the figure yourself and going ahead and allowing the very prevalent technology that we have these days give you a little bit of a hand. Okay, there are simple things that I expect you to be able to graph or know what the graph looks like without doing any work. Okay, this is an example of such a function. Okay, and if you review the chapter 12 material where the textbook talks about quadratic surfaces, those are the things that I expect you to know by just looking at them and having a pretty good idea of what the surface looks like. Okay, that's the purpose of that material, and you can review the later chapter 12 sections if that doesn't make sense to you. Okay, there are other things that are just weird, and we're not going to know what they look like until we ask the computer to give us a hand. Okay, so for instance, this thing. Okay, I wouldn't expect you to know without doing any work what's going on here, right? But there are tools for this. Okay? This is a website called GeoGebra, and what it is pretty good at is doing graphs. Okay, and it has some built-in capabilities to allow you to do three-dimensional graphs. So the function that showed up here is the square root of x plus y plus 1 over x minus 1. So x plus 1 or x minus 1. So it has spit out this surface for us. Okay, I didn't have to do anything more complicated than type in the equation. All right. Now there are some useful shorthands to know. Obviously, you saw me type out SQRT as the abbreviation for square root. That's how I got the square root symbol. And then there are some things you have to learn about how to, like, when to press certain arrow keys to make sure that you're not underneath the radical sign anymore, so you can do something like division, which is what I did. So the keystrokes that I used was SQRT x plus y plus 1, and then right arrow to move the cursor over, and then the division symbol, which made a fraction, and then I typed x minus 1. Okay. If you do something like try to graph something else, okay, we can get some other kind of surface here. Huh? Well, this, okay, it's not actually that bad. All right. Okay, all right, so we need to have this conversation now. Okay, anyway, powerful tools are nice, all right, but you won't be able to use a computer on your exams. So make sure that you are familiar with the basic shapes, the quadratic surfaces that I'm talking about, because those are the ones that are going to show up on exams, because those are the ones that I expect you to be able to work with. Okay. Or simple things like I might give you a function and then ask you questions about that function, but maybe not to graph it if it's something that's complicated or going to be difficult. But we'll work on that. Okay. So let's use that example that I just made up here. All right. G of xy equals x e to the y. If I want to get an idea of what this thing might look like, one of the ways to do that are to create some traces. Okay? Traces are 2D images that allow us to get an idea of what some cross sections of this surface would look like. Okay? So what you can do is say, I want to know what this looks like when z is equal to 0. Okay? I want to know what this looks like when z is equal to 1. Okay? What you can do is you can pick several values, and then by choosing those values, set things up to be able to determine curves at these level sets. Okay? So for this, let me move this around a little bit here. Okay. So we're looking at what's going on in an XY graph by setting z to be some constant value. If z is equal to 0, what I want to do is I want to rewrite this in terms of a function of x or y, right? Problem is, e to the y is never equal to 0. So the only way that's equal to 0 is if x is equal to 0, right? Makes the graph really easy to draw. And that matches, right? You can see how it's just a 0 here. Okay, you see this green line? Yes, the green axis. See how the surface touches that axis at every point? Okay, that means that when z is equal to 0, this is the cross section of the function. So imagine that you have a horizontal plane and you set the height of that plane is equals 0 and you slice through the surface. Okay, you want the curve that you get where you have cut through the surface. That's what we're drawing. Okay, for the next one, we want to rearrange this function here. We would ideally like to get a function of y or something if we can. Divide both sides by x, take the natural log of both sides, it's y by itself. Okay. Okay. Now, this is a little bit harder to see. I need to lift that up. How do I? Okay. So the +1 is not part. No, I can't do that. Need to move it up in the z direction. How do I do that? There. Okay. All right. So what I've done here is because it's possible for me to parameterize this curve as a space curve, where x is the independent variable. X is the first parameter, the second parameter is y, and we know that y is equal to the natural log of 1 over x. And then the height is equals 1, right? This now has that curve that you can see, and you can see that the curve follows along the surface. Oh, whoops, I forgot to switch screens. Sorry about that. Okay, let's go through this again. What I typed in was this. Just this part here. That's all I had to type in. Was x and then natural log of 1 over x and then 1 in parentheses. X, and this is just a space curve. So x is the parameter, this is the function for y, and then this is 1. Okay. And if you have something that you can only write as a function of y instead of a function of x, you can just reverse the roles of these and write it as a function of y and still be able to graph it. This thing's smart enough to do that. The z value is 1. And what we can see is that we have our curve here that is on the surface. Okay. So even if you don't have a powerful computer, what you can do is you can select several values for z and make these traces, all right? And then get an idea, or at least an approximate idea of what the surface would look like based on those traces. Okay? All right. In general, these are also referred to as level sets of the surface. Okay? The images for these traces that we generate. Okay? Who here has gone hiking? Okay. Have you ever used something called a topographical map? Okay. What we're doing here is we are creating a topographical map of the function. All right. The idea is that each of those lines represents a fixed change in altitude, right? And then if you travel at a fixed altitude, you would have to travel along that curve. Okay. We're doing the same thing, just the math class version of it. So that's how all this goes together here. Okay. Now, this isn't something that we use terribly often in this class, but is important for you to know because it may be used in other classes, is that functions can be represented numerically. Okay. Most of the time when we talk about functions, what we'll do is we'll have some domain, a codomain, and a formula, and then we'll use that formula as an assignment operation in order to talk about what the function looks like. And then when we have that information, we can do things like draw pictures, which is what we were just working on, right? Thing is that the computer draws pictures by doing this, right? What it does is it generates a giant table of values based on the assignment operation and then plots in a pretty looking way all of these numbers, or the equivalent numbers for the example that we're looking at. In real world applications, this information is what we can measure. Okay? Nature doesn't tell us mathematical formulas for things. Nature tells us individual measurements, and then we can collect those measurements and then put them into a table and then interpret that table as a mathematical function. Right? If you're doing marketing data for some business, this is what you get, right? If you're doing something like mapping gas prices, okay, you have say time of year and how expensive it is to buy crude oil, right? And then those two parameters would feed into what the gas price at the pump is going to be. Obviously, there are several other things, like whether or not the ports are open. But that's how this will work, right? So know that in a business environment or a professional environment, these are functions too, okay? And if you have classes where you use Excel heavily, all right, it relies pretty significantly on doing this representation of a function. Okay. Here's a more stark visual representation of the idea of level sets we were discussing earlier. Okay, and then of course the contour plots. There's plenty of pretty versions of this. Okay. Next up, we have functions of 3 variables. Okay. Now, for functions of 3 variables, there aren't a lot of material things that change from what we were talking about before and what we're talking about now. Okay. I'm going to have the same kind of thing set up. We'll write that for now. Okay. We're going to take our domain to be a subset of three-dimensional space. Okay. And we are going to have an assignment operation like we had before, except now there are 3 independent variables. Okay. When it comes to working with these pictures, we're now in trouble. Okay. It is not possible for us to, without employing some other means, fully represent the information stored in these types of images if we're mapping 3 dimensions onto 1. Okay, we need to do something else. All right. Now, we're in Kansas. Okay. It's not quite late enough in the spring yet for it to be really heavy storm season, and we've managed to avoid so far the nasty winter storms. But when they show the weather radar on television, what does it look like? A bunch of colors and blobs, right? Now, what do the blobs represent? Okay. What do the colors mean? Okay. So there's 2 kind of conflicting answers here. The pictures that we see in the radar, often now, because, and you'll notice this if you move away from the region, Kansas has the most sophisticated weather prediction technology, or at least is in the neighborhood of some of the most sophisticated weather prediction technology that we have. Because we need it. Tornadoes are scary, all right, and tornadoes happen fast, all right. The places that have hurricanes, they've got days to figure out what they're going to do and then decide not to do it, right? For the tornado folks, we have hours and are usually worried about it. Okay. If you're not from Kansas, by the way, if the sky turns green and the leaves fall straight down, it's time to hide. Okay. All right. Anywho, anyway, for the weather radar pictures, we have nice 3D images. Okay. The 3-dimensional representation of the storm systems and the clouds are spatial representations of where the thing is, right? And then often there's a time lapse that says what happens after, or what has occurred in the past, say 15 minutes to 2 hours or whatever, as the storm system is moved. Okay. There's also a coloring that is used on the images. Okay. And the coloring sometimes means velocity, sometimes it means pressure, occasionally it means how much expected snowfall is in an area. All right. But what I've just talked you through is the ability to represent 5 dimensions worth of information in a fundamentally 3-dimensional environment. Technically 2-dimensional because we're just looking at the 2-dimensional approximation of a 3D representation, right? Because it has to show up on our television screens. But we have to be clever, okay? We can't just use spatial dimensions to represent these things because there's too much information. We have to use color or time lapse or something like that in order to press this information beyond 3 dimensions into the image. Okay. So know that you are going to be working with things in the abstract. Okay. You are not going to be able to fully visualize what it is you're working with, which is part of the reason why understanding the notation and being very careful about what you're doing is so important. All right. There's structure in here to help you overcome that inability to hold all of it in your head. All right. Now, you will, as time goes on, get better at conceptualizing things that are a little bit fuzzier than a strict three-dimensional spatial representation. Okay. Because you'll be able to do things like compare it to those weather radar pictures and hold that in your mind. But the most important thing to do is allow the notation to do the heavy lifting for you and to abstract that information so that you can be focused on the things that you have to know, like which formulas to use, how to do the calculus for the particular problem involved, and things like that, instead of being bogged down by trying to imagine a picture that you literally cannot. Okay? So I have to give up on that a little bit. I apologize to the spatial reasoners among us, but we're talking about fundamental limitations in the evolutionary process that got us to where we are. Okay, we just can't see that many dimensions. All right. So there are some additional examples here. All right, and additional explanations. It's actually not that big of a jump to jump from where we are right now to functions of several variables. Okay, where we map a what's called an n tuple, where we have x independent or n independent variables into a single dependent variable. It doesn't change anything about the notation or the way that we think about it, right? It just becomes harder to draw the picture, even more so. Okay. All right. Questions? Jim's okay? All right. Let's do the short section now. Okay. So 14.2 is about limits and continuity. Okay. There isn't really going to be any surprises here, except we have to just be a little bit more careful due to the fact that we're talking about a multivariate function instead of just a space curve. All right. So the definition introduces some extra vocabulary here in order to try to make it clear what's going on. The basic idea is that if we have a function of two or more variables, and we want to know if the function is continuous at some point in the domain D, then we take that point A, we look at the neighborhoods of A, which are the points in the domain that are close to that point, and we try to make sure that if we are within a neighborhood of A, what we specify is epsilon, which is an error bound. That says the value of the function has to be within epsilon of what you say the limit is. Okay? And if you specify an epsilon, then I can always pick a delta, an input precision that says that if you say that I have to be within epsilon of L, I can tell you what delta you have to be within of A in order to always satisfy that condition. And if for every choice of the error bound epsilon, there is a corresponding choice of input precision, then the limit exists and everything's fine. Right? So visually, what that means is that we have some picture that looks like this. We have our surface okay, and there's our delta domain down here. And what happens is epsilon gives me a height. Okay, epsilon corresponds to height in this picture. Okay, so if you specify the range of heights that the point has to sit in, then what I can do is I can specify the radius delta around the point to say, if you say that I have to be within epsilon, then this is the delta that you have to be within of A. Okay? As long as the point on the surface is always inside that cylinder for any choice of epsilon, the limit exists. Okay? Obviously, as epsilon approaches 0, the size of the cylinder is going to vanish, right? Now, the tricky part about limits in higher dimensions is that we have to be a little bit more careful about how we compute them. Because in order for that condition that I just described to be satisfied, I have to have the same value for the limit regardless of how I approach the point. Okay? Because I can come from an infinite number of directions in 2D, right? There are an infinite number of paths. And that's only counting the paths that are straight lines, right? You can take a radius and then just start changing theta and then go around an infinite number of straight line paths. And then as we can see from the image here on screen, that I have to worry about paths that aren't straight as well. So in one-dimensional limits, we can get away with just worrying about the two-sided limits because in 1D, I can only come in from the left or come in from the right. So it's very easy for me to exhaustively check all possible directions. I add one dimension, suddenly it's impossible. Right? So what we have to do is be a little bit more careful about things. I'm going to lean on the notes here because these pictures are hard to draw. Anyway, so here is an example of a function. We want to look at the limit as we approach the point 1, 0 of the function xy minus y all over x squared, sorry, x minus 1 quantity squared plus y squared. Okay. If you suspect that a limit is not going to exist, what you can do is you can choose particular paths to travel upon. Okay, so for here, we choose the path y equals 0, which means that we can just treat the function as f of x0, plug in y equals 0, and then see what we get. And after evaluation of the limit in this case, we're going to get 0 here, right? Now, by the way, the reason that this denominator is not a problem is because the numerator is always 0, right? Because if I plugged in x equals 1, I would get 1 minus 1. That's bad. Okay, but that can't happen because x is never actually equal to 1, and it's always 0 in the denominator. Remember the limit arithmetic logic? Okay, we have to remember that we often cheat and just plug in the number because of continuity, and continuity is nice. But in a situation like this, we have to remember how limits actually work. We never evaluate it at the point. Okay. The next example is we choose the line y equals x minus 1. The reason that we make that choice is because it makes the denominator really nice. Okay. And it turns out that we get 1/2 here. And in the image, we can see the two limits being indicated and that the limits approach different values. One of the limits is up here on the surface, and the other limit is down here. The way that the picture's turned makes it look like those arrow connections don't quite line up, but they are at the same point in the x and y axis. Okay. And if you're curious about this, you could also graph this function in GeoGebra to get another look at it. Hold on. Sorry, I don't use GeoGebra quite as often as I use some of these other tools. Go away. It was xy minus y divided by x minus 1 squared plus y squared. Okay, we zoom in here. We can see that this is a problem, right? Oh, there's that seam in the function. Okay, that's where we're trying to take the limit. So down here we get 0, up here we get 1/2. Okay. Okay. There's another example here where we have limits that give us divergent values. The trick, of course, is if you suspect, you start picking the paths that look like they might cause problems. Okay, so you just choose lines, usually. Okay, and rarely you'll have one where all of the straight line paths are fine, or all of the obvious straight line paths are fine, and you might have to choose something weird like y equals x squared, and y equals x squared will break it, right? But it should be pretty easy by looking at the function algebraically when that's going to happen. Okay, so a little bit of practice here. This isn't going to be something that we go crazy about, okay? Because we're mostly interested in the places where limits exist because we want to do calculus, right? All right, or at least the parts of calculus that you're taught to think are important, derivatives and integrals, right? Okay, limits are actually the real calculus. Okay, those other things don't work without limits, but that's all right. Okay, in order to prove limits work, for the most part, we more or less have to use the squeeze theorem. Okay, that's our tool. All right, we're actually proving that a limit exists. They're in general difficult enough that doing clever substitutions and using the squeeze theorem is the technique. And there are several exercises here for you to follow along with to sharpen your skills about this. All right. Okay. So before we move on, questions about that? The squeeze theorem is one of the ways that we compute limits. Basically, the idea is that if we have two limits that are the same as we approach a point for two different functions, f and g, and we have a third function that is trapped in between these two functions. We squeeze the function in the middle by using the limits of the other two expressions. So it traps it. If you've never seen it before, then the people who taught your Calculus 1 class did not do what they were supposed to do. But there's, yeah, that one, the third one does it, yeah. Okay, so the third one uses the squeeze theorem. So example 3, or exercise 3 here on the notes. All right. Okay. And here's the most important part of the section. Continuity works the way that you want it to. Okay. If a function is equal to its limit at a point, it is continuous at that point. If a function is continuous at a domain full of points, then we say that it's continuous on that domain, right? And as we all remember from our previous calculus classes, continuity is one of the requirements for differentiability. Okay, differentiability is a harder condition to satisfy than continuity, but continuity is necessary. Okay. We also, in situations where we know certain types of functions are continuous, get to use those evaluations to help us compute their limits. Okay. Polynomials are still continuous everywhere, even if they're polynomials of two variables. Right? You can just think of them as the products or a combination of two one-dimensional polynomials. All right, but it has to be the same thing. Rational functions obey the same properties. Okay, rational functions, because they're a polynomial divided by another polynomial, are going to be continuous everywhere except for where the denominator is equal to 0. And you can use the continuity properties to help you evaluate the limits as well. Make sense? Okay, so in general, for these purposes unless we absolutely 100% for certain have to prove that a limit of a higher dimensional function is equal to a certain value, we rely on continuity properties unless the continuity properties don't help us. Okay? Like we had some earlier examples where the function failed to be continuous, right? Or there was a gap in the function. It might still have a limit, even if a function's not defined at a point, right? That's when we have to do something like use the squeeze theorem. Like for this thing. That's not continuous at 0, 0. Because the denominator is equal to 0, right? Which is why we have to rely on the other technique. Yes. Okay, yeah. So is this the example you were talking about? Oh, okay. Oh, this one? All right. Okay, so that picture and this picture go together. So this is the spot you're talking about here. Again, the perspective is a little bit weird, but we'll look at this picture. We can still have asymptotes, okay? Asymptotes or asymptotic behavior is more correctly thought of in terms of limits than it is in terms of it being some line, okay? So if you recall, an asymptote is the line, all right? But what really is more important to think about is asymptotic behavior. So in the one-dimensional case, this is the definition of what it means for something to have an asymptote, right? If I approach from the left or from the right, or a vertical asymptote in this case in particular, if I approach a value from the left or from the right, and I get either positive infinity or negative infinity, then that means that the function has to do one of those things, all right? In a situation where we're traveling on a surface, there are way more than two directions to worry about, okay? The actual idea of an asymptote is a little bit tough, but you mostly care about whether the value of the function blows up towards infinity or negative infinity. As you see in this image here, looks like in most instances, it's firing down towards negative infinity as it gets close to that trouble spot. There's like a crease, but it's more helpful to think about traveling along the surface than trying to add a plane or a line to in addition to this drawing. So like the way that I think about it is if I'm like in a car driving along, I try to see what happens to me as I get close to the abyss here, right? I mean this. Okay, so this is just kind of a crease in the surface. It doesn't have, so like you could definitely say that this would be that the surface is bounded above by a plane that sits level there. Yeah. And without doing the math, I can't necessarily say that this is asymptotic, but it may very well be, right? If I get arbitrarily close to some plane that just sits, like is a shelf on top of this surface, then that would also count as approaching something asymptotically in certain directions. But once we peel away, or once we move into higher dimensions, we don't have kind of rigid definitions about asymptotes necessarily, because we have to describe them in terms of planes or other types of objects, which necessarily is a little bit more difficult. Anyway, but thank you for the question. Okay, so there will be a quiz for this week's stuff. Okay, it'll cover, I think, 13.4 in the first couple sections of 14, as we talked about. I'll get that posted later on today sometimes. I don't know if I have office stuff that I have to do. It'll prevent me from getting to where the computer where all that stuff is saved. So anyway, but it'll be up at least by tomorrow. And then I wish you all a wonderful weekend. Take care of yourselves, and we'll come back and continue on next week.